Problem 2 asks us to imagine rubbing our hands together to try to generate heat. And this is a Fermi problem. It's going to require us to estimate a lot of things. But the general approach that we're going to take is to use the work-energy theorem. We know that work is the dot product of force with displacement. And in this case, the frictional force from our hands being rubbed together is always opposing the motion. So this is always negative. This is going to be minus the force of friction times the displacement, which this is kinetic friction since you're rubbing something. So this is going to be minus mu k times the normal force times however far you displace your hands past each other in 10 seconds. So how do we estimate this? Well, we need to estimate a coefficient of friction, we need to estimate a normal force, and we need to estimate the displacement. Again, these numbers don't have to be exactly the same. I'm going to estimate that the coefficient of friction for skin on skin is about 1/2. It could be more depending on the condition of your fingerprints, how dry your hands are, how oily they are, things like that. The normal force, how hard you can press your hands together. Well, I figure about 10 pounds force is reasonable. I'm kind of thinking about, how much weight you could easily manipulate with one hand. That's the weight of about 5 kilograms, which is about 50 newtons. And then how far can you move your hands in 10 seconds? Well, a reasonable speed for you to be moving them might be 1 meter per second. If you're moving them very, very quickly to try to generate a lot of heat, I imagine that you're outside and very cold in the Syracuse winter. So if you're moving them at about 1 meter per second, the total displacement as a high-end estimate might be 10 meters. Ten seconds at 1 meter per second. So that means, putting all this together, the work from friction is minus 0.5 times a normal force of 50 newtons times a total displacement of 10 meters. Again, you're moving your hands up and then back and then up and then back, so you're moving them further than you think you are. This gives us 250 joules minus 250 joules of work, or plus 250 joules of heat. Now, if I'm thinking about this in mechanical power, 250 joules over 10 seconds is 25 watts. I know that the power output of like a fit human on a bicycle that they could sustain for a long time is a couple hundred watts. So 25 watts generated with my arms rubbing past each other, that's maybe 1/10 of what you might do on an exercise bike for a long time. So that's reasonable. We're in the right ballpark of the kind of power you can put out with your arms. Oops. I'm going to write this estimate down because another way to do this problem that I know some of you have done is to use the relation power equals force times velocity to estimate this and then multiply by time. That works as well. Part B of this problem asks us to try to figure out how effective this would be at warming your hands up. So I know that the value that I've been given for the specific heat of tissue, how much heat it takes to raise the temperature of tissue, is 4 joules per gram per degree. So I'm going to need to estimate the mass of my hands. Now, if I'm trying to warm up my hands, this is only going to get my palms warm. So the fact that my hands aren't like monolithic, that different parts of my hands will be at different temperature, um, isn't quite true. I just tried this here, and if I rub my hands together for 10 seconds, I can actually get just the surface of my skin hot enough that it gets uncomfortable. But here we're going to take our entire hand as one unit. So one hand. We'll say that the mass of a hand is maybe 200 grams. Depends on if you have big hands or small hands. So if I need 4 joules per gram per degree, I've got 4, well, we should actually start with the amount of energy. So I want the temp change. That's going to be equal to the amount of energy I have, so 250 joules divided by this heat capacity value that I have. So 4 joules per gram per degree. Now, through the magic of canceling out units, I can cancel my joules. Remember, that is divided. I also need to divide by the mass of a hand. So dividing the grams out. If you're confused by the fractions that I've done, flip them and multiply. Again, joules divided by joules cancels, and divided by grams in the denominator, and then divided by grams also cancels. Again, if you're confused by the fractions, flip the division signs and multiply. Flip the fractions and change the division signs to multiplication signs, you know what I mean. So taking all these numbers together, I'll actually do this in the next line. So I have 250 joules times, I'm going to flip and multiply, grams degrees Celsius over 4 joules times 1 over 200 grams. This is the mass of a hand. The reason I'm writing this out with numbers is to show you how, even if you don't know the formula for something, Fermi estimation lets you figure it out just by thinking about the units things are measured in. Joules cancel, grams cancel. I have 250 divided by 4 times 200. So how much can this lift the temperature of my hands? That's 250 over 800 degrees Celsius. That number is, let's see, it's a little bit more than, because 200 over 800 would be a quarter. This is going to be a bit more than a quarter. So this is about 0.325 degrees Celsius. So this is an interesting result, because I saw empirically that in 10 seconds of rubbing my hands together, I can increase the temperature of my entire hand by about 1/3 of a degree. It's enough to really increase the temperature of my skin, because that heat is not broadly dispersed through my hands. So if I get 1/3 of a degree for my whole hand taken as an average, then this has no chance of warming my body up all that much overall.